This is going to be lathe 102. Here we're going to start talking about some of the alignment, accuracy and calibration, and capacities of how they're measured on a lathe. One thing that you do normally start with on a much larger lathe is by leveling the bed. So what you want to make sure is that this portion of the bed is in the exact same plane as the end and that there is no twisting along the bed. On a larger lathe, you would then place shims underneath the corners to get that level. On a small lathe like this, start with just mounting it to a good board. There's not a lot of weight here to cause twisting. You would think on a machine that weighs 400 or 500 pounds plus that it's not going to twist, but they do. In order to measure that twist, you have to use a machinist's level. This is not a torpedo level. This is not a level you're going to pick up at your local home center. These usually cost in excess of $100. They're not a cheap investment. I really don't think you need them on a lathe this size. I did measure, so you just basically place the level at different points along the bed and check to see how level it is or what the variance in levelness is from one end to the other end of the bed. This is dead on. I was actually kind of surprised at how close it was. So that's good news and impressive to state that this is a very well built bed and ways. So I should have started out mentioning this, but I do want to state that whether you're buying a $200 lathe or a $700 lathe or a $20,000 lathe, you do need to do this type of setup and calibration and alignment. Depending on the quality of the lathe and what you do with it will dictate on how often you have to redo those calibrations. But this is a critical step no matter which lathe you get. Out of the box, you're going to have some alignment issues, hopefully very few and very minor, but they are steps that you have to take to check. Next item we're going to do, and the reason why I suggest you have dead centers, is we're going to align the headstock spindle with the tailstock spindle. And we do this by inserting the centers in. I've moved the cross slide as close as I can to the head. Be careful because even though there looks like there's still some space here, there is a Gibb in the back that you don't want to be running into the head. So we're going to bring this up as close as we can and find the right hex key to tighten it down. You don't want to leave this loose, because with it tight, it is going to move slightly. Now we're going to extend the ram. And then once the ram is fully extended, we want these points to be as close as possible to each other. We're just going to do a visual inspection on these. You do want to tighten down the lock on the ram as well. And you'll want to do an inspection looking down as well as at the side. So I moved the camera in as close as I can get with this particular lens to see how far off those points are. I am elevated up still a little bit. I should be down a little bit lower, but it looks to me like the tailstock is running slightly high. Then again, we would do another view looking straight down to see if there's any offset forward or back between these 2 points. So left to right, it appears to be dead on. From what I can see. This does again appear slightly high, which depending on what you're doing, that could be problematic. You could shim the tailstock. One thing to realize is that slight high is going to be over a distance, whether that be the full length of the bed being 17 inches or 5 inches. And in that case, that variance over that length is pretty minimal and really not that critical. So we're going to just leave it as is. That's good enough for what I want to do. You can adjust the Gibb slightly underneath here with a couple of screws on top and bottom to help give it a little bit of an up and down. Now this is a visual inspection of alignment only. To truly determine how far off they are, what you would end up doing is you'd create a test bar. And I'm not going to show the process for a test bar here. And the next step that we're going to do in the alignment is aligning the cutting tool to center height. This is important both for safety as well as a fine finish, and when you're doing facing operations, which we'll talk about later, you want it as close to center to actually be able to face the full piece off. Having it a little bit below center is probably safer than starting above center, just to give you that adjustment up rather than down. So you can adjust this visually as we're doing here, which all we care about is the vertical placement. So how close is this point and this point as far as height goes? They do make a height gauge as well that will set on the bed or the ways of the lathe, and then you basically lift this to an underside surface of that height gauge if you want to use it. You can also make your own, or there are adjustable ones so that you can set it and then forget it, so that you can quickly align a tool here. The best way to test this alignment is with turning, doing a facing operation all the way to the center. If there's a little nub left at the end, then you know you're still slightly low and need to bring the height up. That's really all there is to the alignment on a lathe. Next, we're going to start looking at some of the accuracies and how we measure those accuracies on the lathe. So to begin testing the accuracy of the lathe, and mainly we're going to look at the lathe spindle and some chucks here, you're going to need a good dial indicator, and I do recommend a swing arm style rather than a plunge style. So here are two examples. In the front is a star at last word, definitely a very high quality swing arm, and this is the one we're going to use because it has a lot of the attachments we need, and is again the higher quality of what's shown here. If you're on more of a budget, then a unit like this Grizzly will work just as well for the majority of the operations that we're going to do here. The drawback on the Grizzly is you're going to probably have to come up with different ways of holding this. The star does come in a kit with all the items we'll need to do work holding here. To begin checking the accuracy of the machine, I'm going to start with the outside of the spindle. This isn't a surface you'll actually reference to, but it is just a good idea to get a measurement off of it. The better measurement, which we'll take next, is the inside of the spindle. So here, I'm just going to rotate the spindle by hand at first. You want to make sure you're on a spot of the lathe spindle that isn't going to drop into that hole or be affected by any burrs on that hole. Once you've rotated it by hand a little bit, then you can go ahead and turn it on at a low speed. And we can get a good idea of the variance on the outside of that. So here we're running, looks like a 1/2 thousandth or less, so not very bad. I think that's well within their specs. We'd have to check the site, but definitely for a machine in this price range, that is well within spec. Now if you start going to a higher dollar range, you're going to be able to start getting beyond the measurement capacities of this dial indicator into the 0.0002, so 2/10 of a thousandth or 2/10,000ths, and the cost of those just skyrocket. You'll spend as much on a single collet for a device like that, not a collet holder, not a chuck, but just the collet itself. You'll spend $700, $800 easily to get that type of precision, which is more than the cost of this entire lathe. So definitely this is a very, very acceptable amount. One other thing that I wanted to note is what is precision and how much variance are we getting here? So according to some research that I did, human hair, depending on genetics and the area in the world you're in and the part of the body it comes from, the thinnest human hairs are 2/1000ths of an inch thick. So this is less than a quarter of that. Thicker human hairs can go all the way up to 6/1000ths of an inch. So we have very, very, very little deviation here. This is a very good sign. Okay, since I had the center in there, I thought I'd go ahead and indicate off the body of the center, and we'll indicate off the tip of it next. We're again within very, very close tolerances there. Roughly, again, a 1/2 thousandth. So very, very minimal run out. So now we're indicating on the very tip, or close to the very tip of that center, and we are seeing a little bit more swing. With the way it's jumping and when hand turning it, that swing is actually a scratch that I probably put on the center that's causing that jump. But we are jumping up to about 1.5, so 1.5 thousandths with that scratch in there. This kind of brings up the point of definitely taking care of your tools, putting them in ways where they can't bang into each other or scratch into each other. So this is something that kind of a lesson learned here. If you need ultra precision, you need to take ultra good care of your tools. So now I've moved the indicator to where we're checking the inside dimension of the spindle. This is really the critical dimension for accuracy, because if you're using a collet or any sort of a taper, it's going to register off of that inside diameter, and that's what you really want to have as precise as possible. Anything that's threaded is going to induce error. That's just a nature of the way threads are, that can be reduced in certain ways, but a taper is by far the most accurate way. And if you look at this, I mean, this is a running video, that needle is hardly moving at all. I would definitely say that spindle right now is running, we're well under 1/2 thousandth. It's barely moving at all. Over time, the bearings are going to wear, and you are going to see those numbers increase. That's the case with any machine. You can get higher quality replacement bearings if you want. You're going to get to the point where, again, you can spend $300, $400, $500, $600 on just replacement bearings for the headstock. So I think that Sherline has done a really good job here of balancing accuracy. So now I have their 3-jaw self-centering chuck on here, and inside the chuck I have a piece of 3/8 inch 01 tool steel drill rod, so it's a precision ground rod. And we're measuring as close to the jaws as we possibly can to make sure that there's no bend or misalignment in the bar itself. We're running about 4 thousandths here, maybe a hair over. A 3-jaw self-centering or any self-centering chuck isn't meant for super precision. It's meant for speed and ease more than anything else. If you want higher precision, go to a 4 or a 6-jaw chuck that is not self-centering, or go to a collet for the pieces that will fit in a collet that are smaller. Now, as we move further out away from the chuck, this should magnify any imperfections in the jaw of the chuck, or any pieces of dirt or grit that I might have gotten in there while chucking the piece. But at this point, it's running pretty much exactly the same as it was close to the jaws. So this is, again, a good indication of the accuracy of these jaws. So this last test that we're going to do is that same 3/8 inch drill rod, but this time in a chuck, a drill chuck. This is not a method I would recommend for work holding. If you're wanting to put a polishing stone or something on there like that, you could do that, or polishing rag, buff, well, things along those lines. But these chucks were not really meant for horizontal operation, so pressing against them is going to destroy them fairly quickly, and as we're about to see, their accuracy is also very low. So you really want to just mostly do drilling operations with these, and you'll see why the accuracy of them are not, the accuracy of a drilled hole is not the greatest. So with this, we're swinging about 8.5, 9 thousandths of an inch. Quite a bit more than anything we've looked at before, anywhere from double to a little bit over of the 3-jaw chuck, which again, the 3-jaw is not really a precision chuck, and significantly more than the inside of the spindle or even the outside of the spindle. So let's again move further away, and that increased a little bit. We're swinging a little bit lower on the 0 side to get a good measurement. The best way, because sometimes seeing the end number there is a little difficult, is just turn the spindle by hand. So there we are definitely exceeding 9 thousandths. But again, it's a drill chuck. Drill chucks are not made for precision. Do not expect them to be precise. Use the proper tool holders. So we've talked about alignment and accuracy at this point. Both alignment and accuracy on this were pretty good out of the box, I would say. Again, it's a new. As things wear, you're going to start to degrade those accuracies. That's just part of metal machining and the hardness of the metal and metal rubbing against metal. So next up, let's talk about how capacities are measured. So the 3.5 inch measurement is referring to the swing over the bed. If we were to put a center in there and get a precise measurement, the distance to the center of the spindle would be roughly 1.75 inches or larger. Double that and you get to the 3.5 inch, which is the maximum size of swing that you can do on this lathe. There are riser blocks, so you can get riser blocks from Sherline that do increase that capacity number up to 6 inches. To give you another kind of visual example of that, if we were to put the chuck back on, this chuck is roughly 3.1 inches in diameter, so you can see there's not a lot of space beyond a size this piece that you could fit on the lathe without the riser blocks. So the next number is the distance between centers. I don't have this extended all the way, but from this center point to this center point with the unit extended all the way out, you'd be looking at a 17-inch length. The reason that you might want some of that extra length is not because you're going to necessarily turn a 17-inch long piece, but because as you start to put drill chucks in here and 3-jaw or 4-jaw chucks in here, you really start to eat up the space that you have with the tooling that you're installing. We're going to talk about these tapers. So there's a very slight taper on here. This is a Morse taper 1 compared to the tailstock is a Morse taper 0. These tapers go on up in size and larger and larger. The larger the mill you have, the larger the taper you're going to be able to hold. You can then put adapters into in a Morse 3 taper to hold a Morse 1 or a Morse 0. It just gives you more flexibility and capacity with tooling. Additionally, the diameter that goes all the way through the spindle is going to give you some capacity capabilities and limitations, in that if you have a long piece like this, but you're wanting to do some small work on the face of it with the through spindle, you could, obviously I don't have a chuck on here or collet, but you could push that through the head and just be working on the face. Whereas if you're dealing with a larger diameter piece, you would have to have it extended out here and just the end held by the chuck. At that point, for this type of operation, if there was no way to hold this end, you'd need to use a steady rest or other method to keep this from just flopping all over the place. So I haven't checked the official specification on the Sherline website, but a measurement of the spindle here is indicating that it's 0.4 inches on inner diameter, which means if we go back to that previous rod that we were working with, that's a 3/8 inch rod. In decimal, it's 0.375. That would probably be one of the larger capacities that we're going to be able to work with longer stock through the spindle on. So other capacities to consider when you're looking at a lathe is the size of the cross table and how much travel the cross table has. For my uses, that's not really a limiting factor, and this cross slide is definitely big enough for everything I need to do on a lathe this size. It comes more into play on a mill where you're moving the workpiece around quite a bit more and not dealing with necessarily cylindrical or square long items like you do here.